Have you ever stopped to think about the magic that happens between the wall socket and your phone? We're about to pull back the curtain on a technology that powers pretty much everything in your life, from your car to the entire internet. But it stays almost completely invisible. This is the story of the unseen engine of our modern world, power electronics.
All right, let's just jump right in with a question you've probably wondered about. You look at your phone charger, that bulky power brick for your laptop, that little box on the cord for your TV. Why can't you just plug them straight into the wall? What is actually going on inside those little black boxes?
Well, the answer is a whole field of engineering called power electronics. The best way to think about it is as an electrical translator. The power coming out of your wall is like a foreign language to the power your phone actually needs to charge. Power electronics is that crucial piece of technology that bridges the gap, taking one kind of electricity and efficiently converting it into another.
And here's the amazing part. This entire, incredibly complex field, it all boils down to mastering one simple but really powerful idea: the concept of a perfect electrical switch. Seriously, everything we're about to talk about builds on this one foundational idea. Now, when I say switch, you're probably picturing a light switch on the wall, right? That's a mechanical switch. It's slow, there are physical parts that click together, and eventually they wear out. But in power electronics, we use something way more advanced: the power transistor. It is the exact opposite. It's pure electronics. There are no moving parts, and it's capable of switching on and off millions of times per second without ever breaking a sweat.
And this quote on screen, it really gets to the heart of it. These little semiconductor switches are the fundamental building blocks. By controlling them with unbelievable speed and precision, engineers can manage exactly how much energy flows through a circuit. It's like having a microscopic, lightning-fast gatekeeper for electricity.
So, let's meet one of the stars of the show. This is the MOSFET. It's one of the most common power transistors out there, and it's essentially a voltage-controlled switch that can fire millions of times a second. Think of it like an incredibly precise, super-intelligent faucet for electricity. You apply a tiny electrical signal to one part, and it instantly opens or closes the flow for a much, much larger current. It's the silent workhorse inside countless devices you own.
Okay, but what happens when you need to handle some serious power? Well, then you scale up to something like this, the IGBT. It's a really clever hybrid. It basically combines the fast switching of one kind of transistor with the high-power muscle of another. And the result is a single component that can act as a heavy-duty switch for huge amounts of energy. So while a MOSFET might be perfect for your phone charger, the IGBT is the powerhouse you'd find controlling the motor in an electric car.
All right, so we've got these incredible, super fast switches, but how do we get from a simple on-off component to actually, converting power for your laptop? How does just flicking a switch millions of times a second change the very nature of electricity?
Well, the secret is that they don't work alone. Engineers combine these switches with other components, things like inductors that store energy in magnetic fields, and capacitors that store it in electric fields, into these clever circuits called converters. You can think of it as a whole team of components, all working in perfect sync to literally reshape the flow of electricity.
Let's look at how this works in a basic step-up converter. It's like a little four-step dance. Step 1, the switch closes, and energy starts flowing into an inductor. Step 2, that energy gets stored up in a magnetic field. Then, Step 3, the switch suddenly snaps open. The magnetic field collapses and it has to release all that stored energy at once. And in Step 4, with nowhere else to go, that burst of energy flows to the output, but now at a higher voltage. Now imagine doing that dance thousands or even millions of times per second, and you get a stable, higher voltage supply.
And by arranging these switches and components in different patterns, engineers have a whole toolbox of converters they can build. A great example is the buck-boost regulator. It's a real electrical chameleon. It can step voltage up, it can step it down, or it can even flip it from positive to negative. That kind of versatility is what makes power electronics so incredibly useful.
But we're moving way beyond just the little power brick for your laptop. This same fundamental technology of switching electricity really, really fast is scaling up to manage the power that runs our entire civilization. Just take a look at this list. Power electronics are the heart and soul of electric vehicle motor drives, controlling the energy flowing from the battery to the wheels. They're absolutely essential for renewable energy, converting the kind of messy power from solar panels or wind turbines into the clean, stable power our grid needs. They keep our data centers online, they power massive MRIs, they run heavy industrial equipment. They are truly everywhere.
So it all sounds perfect, right? Well, there's a catch.
There's one huge challenge that defines this entire field, and this quote says it all. Removing heat represents a high cost of equipment. In the world of power electronics, heat is the ultimate enemy.
So how do you fight that enemy? With hardware that looks like this. These finned metal things are called heat sinks. And we need them because even though our switches are incredibly efficient, they're not quite perfect. Every single time a switch flips on or off, a tiny puff of energy is wasted as heat. But multiply that tiny puff by millions of times per second, and you have a very serious thermal problem that you have to solve.
And to put that into perspective for you, this number, 150 degrees Celsius, which is about 300 degrees Fahrenheit, that's the maximum internal temperature a lot of these devices can handle before they just fail. They are operating right on the ragged edge of self-destruction, which makes getting rid of that heat absolutely critical.
So this really brings us to the grand challenge for every single power electronics engineer. The push is always to make everything smaller, faster, and more efficient. But every single one of those goals makes the heat problem even worse. It's this fundamental trade-off, a constant battle against the laws of physics.
Okay, so let's do a quick recap of the key takeaways here. First, power electronics is all about using ultra-fast semiconductor switches to control electricity. Second, we combine these switches into circuits called converters that can change voltage and current. Third, this tech is absolutely vital for, well, everything, from our chargers to massive systems like EVs and renewable energy. And finally, the #1 engineering challenge in this whole field is managing waste heat. So, I'll leave you with this question to think about. As we move towards a world that relies more and more on electricity to solve our biggest problems, like climate change and sustainable transportation, the efficiency of these tiny, unseen switches becomes more important than ever. The next huge breakthrough in energy might not be a giant new power plant, but a tiny, nearly perfect switch. So how will that shape the future that we all build together?